Hi everyone and welcome to today's video. If you're studying computer science, especially at the AS or A level, you've probably heard the term databases thrown about quite a lot. But what exactly are databases and why are they so important? Well, in this video, we're going to break it all down for you. We'll cover everything from the basics of what databases are, how they're structured, and even how to design your own. So by the end of this video, you'll have a solid understanding of databases and how they work. So let's dive in. Let's start with the basics. What is a database? Simply put, a database is an organized collection of data. Think of it like a digital filing cabinet where information is stored in a structured way so that it can be easily accessed, managed, and updated. Databases are everywhere. They're used in hospitals to track patient records, in schools to manage student information, and even in online shopping platforms to store product details. For example, imagine a hospital database. It might store information about patients, their medical histories, and upcoming appointments. Without a database, managing all this information would be chaotic and time consuming. But with a database, the hospital can quickly retrieve a patient's records, update their information, or schedule new appointments, all with just a few clicks. So, in short, a database is a system that helps us store and manage data efficiently. And as we'll see later, there are different types of databases, each suited for different kinds of tasks. Let's talk about one of the most simplest types of databases, the flat file database. A flat file database stores all its data in a single table or file. You've probably worked with a flat file database before without even realizing it, like a CSV file, which is just a list of data separated by commas. For example, imagine a CSV file that lists employees in a company. Each row might contain an employee's name, their role, and their contact details. This kind of database is great for simple tasks like keeping track of small number of employees. But as you can see, flat file databases have some serious limitations. First, they can lead to data duplication. If you have multiple entries for the same employee, you might end up with inconsistent data. Second, the flat file database don't scale well. If you have a lot of data, searching through a single table can become slow and inefficient. And finally, they don't support complex queries, like finding all employees who work in a specific department and have been with the company for more than 5 years. So while flat file databases are easy to use, they're not ideal for managing large or complex datasets. That's where relational databases come in. Relational databases are a step up from the flat file databases. Instead of storing all the data in one big table, relational databases organize data into multiple tables, and these tables are linked together through relationships. This makes it much easier to manage large amounts of data and perform complex queries. Let's take a school database as an example. You might have one table for students, another for courses, and another for teachers. Each table contains specific information like student names, course titles, or teacher contact details. But here's the clever part. These tables are connected through keys. For example, the students table might have a course ID, a field that links each student to a specific course in the courses table. This structure allows you to ask complex questions like which students are enrolled in Mr. Smith's math class or how many students are taking more than 3 courses. And because the data is spread across multiple tables, there's less duplication and the database is more efficient. So in summary, relational databases are powerful tools for managing complex data, and they are widely used in everything from schools to online shopping platforms. Before we can go any further, let's make sure we're all on the same page with some key database terms. These are the building blocks of any databases, so it's important to understand them. First, we have entities. An entity is a distinct object, concept, or event that we want to store data about. For example, in a school database, the entities might be students, courses, and teachers. Next, we have attributes. Attributes are the properties or characteristics of an entity. For example, a student entity might have attributes like name, age, and grade. Then there's the primary key. This is a unique identifier for each record in a table. For example, in a students table, each student might have a unique student ID. This ensures that no two students have the same ID, which helps prevent confusion and errors. We also have foreign keys. A foreign key is a field in one table that links to the primary key in another table. For example, if we have a courses table, it might have a teacher ID field that links to the teachers table. This creates a relationship between the two tables. Finally, there's the secondary key. This is an indexed field which allows for quick searches. For example, in a products table, you might use the product name as a secondary key to quickly find all products with the specific name. So to recap, entities are the things we're storing data about. Attributes are their properties. Primary keys uniquely identify records. Foreign keys link tables together. And secondary keys help us search for data efficiently. A primary key ensures each record in a table is unique and identifiable. It is a unique attribute or combination of attributes that distinguishes a record. For example, student ID in a student table is a primary key. The significance of a primary key is that it prevents duplication and ensures data integrity. Without a primary key, it would be challenging to uniquely identify and manage records in a table. A composite primary key combines two or more attributes to uniquely identify a record. It is a primary key made up of multiple fields. For example, in an order line table, the combination of order ID and line number ensures each order line is unique. This is useful when a single attribute is not sufficient to uniquely identify a record. Secondary keys enable efficient searches by indexing fields other than the primary key. An indexed attribute is used for optimized querying. For example, searching products by category or brand in a product table. In real-world cases, e-commerce platforms allow product searches using various filters such as brand or price range. This makes it easier to find specific items quickly. There are different types of relationships in databases. One-to-one. A single record in one table links to a single record in another. For example, a person and their passport. One to many. So one record in a table relates to multiple records in another. For example, a teacher and their students. Many to many. So multiple records in one table relate to multiple records in another. For example, students and the courses they enroll in. Understanding these relationships is essential for designing efficient and effective databases. Now that we've covered the basics, let's talk about how we can visualize the structure of a database. This is where entity relationship diagrams, or ERDs, come in. An ERD is a graphical representation of the entities in a database and how they relate to each other. For example, let's say we're designing a database for a hotel. We might have entities like guests, room, and bookings. In an ERD, each entity is represented by a rectangle, and the relationships between them are shown with lines. For example, a line between guests and bookings might show that one guest can make multiple bookings, while a line between rooms and bookings might show that each booking is for one specific room. ERDs are incredibly useful when designing a database because they can help you see how everything fits together. They also make it easier to spot potential problems like missing relationships or redundant data. So, if you're ever tasked with designing a database, start by drawing an ERD. It will save you a lot of time and headaches down the line. We can see from the example on our screen that one school has many pupils, or many pupils attend one school. Designing a database involves several steps. Here are a list of steps that you may want to consider. Identify entities and their attributes, establish relationships between entities, normalize tables to reduce redundancy, and create ERDs to help visualize relationships. For example, a hotel database might have tables for guests, rooms, and bookings. By following these steps, you can create a well-structured and efficient database. To create a relationship between customer and subscription, we need to include customer ID in the entity description of subscription. For example, we can see from the subscription we would need sub ID, starter ID, end date, customer ID, and product ID. Here, customer ID and product ID are foreign keys in the subscription table, shown in italics. A foreign key always goes on the many side of relationships. This ensures that the relationship between the tables is properly defined and maintained. Normalization organizes data to reduce redundancy and dependency, improving efficiency. It is a process of structuring tables to ensure consistency and reduce duplication. For example, splitting a combined orders and products table into separate tables with a linking line items table. This helps in maintaining data integrity and optimizing database performance. So the goal is to make sure that each piece of data is stored only in one place, which helps prevent inconsistencies and makes the database easier to maintain. For example, imagine you have a table that combines orders and products. Each order might include details about the customer, the products they've bought, and the price of each product. But this can lead to duplication, like storing the same product name multiple times for different orders. To fix this, we can split the table into smaller, more focused tables. We might have one table for orders, another for products, and the third for line items that links the two. This way, each product name is stored only once, and we can easily update it if needed. Normalization can be a bit tricky to get your head around at first, but it is an essential part of database design. It ensures that your database is efficient, consistent, and easy to work with. Finally, let's talk about referential integrity. This is a concept that ensures the relationships between tables remain consistent. In other words, it prevents you from creating invalid references between tables. For example, imagine you have a university database with tables for students and courses. Each student is enrolled in one or more courses, and this relationship is maintained using foreign keys. Referential integrity ensures that you can't enroll a student in a course that doesn't exist. If you try to do that, the database will throw an error. This might sound like a small thing, but it's actually incredibly important. Without referential integrity, your database could quickly become a mess of broken links and inconsistent data. So always make sure your database enforces referential integrity. It will save you a lot of trouble in the long run. Let's dive a bit deeper into referential integrity because it's such an important concept. Referential integrity ensures that the relationships between tables remain consistent. In other words, it prevents you from creating invalid references between tables. For example, let's say you have a university database with tables for students and courses. Each student is enrolled in one or more courses, and this relationship is maintained using foreign keys. Referential integrity ensures that you can't enroll a student in a course that doesn't exist. If you try to do that, the database will throw an error. This is a repetition of what I've mentioned in the previous slide, but this is an extremely important concept that we try to understand and remember. Here's another example. Imagine you have a customer table and a subscription table. The subscription table has a foreign key that links to the customer table. Referential integrity ensures that you can't add a subscription for a customer who doesn't exist in the customer table. So if you try to add a subscription for a customer with ID C100, but there's no record for C100 in the customer table, the database will prevent you from doing that. Again, this might seem like a small thing, but it's actually incredibly important. Without referential integrity, your database could quickly become a mess of broken links and inconsistent data. So always make sure your database enforces referential integrity. It will save you a lot of trouble in the future. Let's look at a practical example to tie all these concepts together. Imagine we're designing a database for a subscription service called Revision Subs. This service allows customers to subscribe to different revision materials like textbooks and online courses. In this database, we have three main entities: customer, product, and subscription. Each of these entities has its own attributes. For example, the customer table might have attributes like customer ID, name, and email. The product table might have attributes like product ID, name, and price. And the subscription table might have attributes like sub ID, start date, end date, customer ID, and product ID. Notice how the subscription table includes customer ID and product ID as foreign keys. These foreign keys link the subscription table to the customer and product tables, creating relationships between them. This allows us to track which customers have subscribed to which products. Let's say we have a customer with an ID C100 who subscribes to a product with ID P200. The subscription table would record this relationship by storing C100 and P200 in the customer ID and product ID fields respectively. This way, we can easily query the database to find out which products a customer has subscribed to, or which customers have subscribed to a particular product. This is a great example of how relational databases work in practice. By breaking down the data into separate tables and using foreign keys to link them, we can manage complex relationships efficiently and avoid data duplication. Let's talk about many-to-many relationships. This is a type of relationship where multiple records in one table are related to multiple records in another table. For example, think about students and courses. One student can enroll in many courses, and one course can have many students. This is a classic many-to-many relationships. But here's the catch. In a relational database, you can't directly link two tables in a many-to-many relationships. Why? Because it would create lots of problems. For example, if you try to link the customer and product tables directly, you would end up with a situation where you'd need multiple fields in the customer table to hold the product IDs of all the products a customer has bought. But how many fields would you allow? What if a customer buys more products than you've allowed fields for? It quickly becomes messy and impractical. So we can see on this slide that this linking or this configuration does not work. So how do we handle many-to-many relationships? The answer is we use a linking table. This is an extra table that sits between two tables you want to link. For example, if you have a customer table and a product table, you'd create a subscription or a subscription table that links the two. The subscription table would contain the primary keys of both the customer and product tables as foreign keys. This way, you can easily track which customers have bought or have subscribed to which products without duplicating data or creating a tangled mess. Let's take another example. Imagine a gym database where you have a table for members and a table for classes. A member can attend many classes, and a class can have many members. To handle this, you'd create a linking table. Let's call it member classes that records which members are attending which classes. This linking table would have foreign keys pointing to the members and classes tables, allowing you to easily query which members are in which classes or which classes a particular member is attending. So, to summarize, many-to-many relationships can't be directly represented in database tables. Instead, you need a linking table to manage the relationship between the two entities. Let's revisit the concept of linking tables again. In many-to-many relationships, because it's such an important part of database design, as we discussed earlier, many-to-many relationships can't be directly represented in database tables. Instead, we use a linking table to manage the relationship between the two entities. For example, let's go back to our gym database or the example of it. We have a table for members and a table for classes. A member can attend many classes and a class can have many members. To handle this, we create a linking table, such as member classes, that records which members are attending which classes. The member classes table would have two foreign keys, one pointing to the members table, let's call it member ID, and one pointing to the classes table, let's call it class ID. This way, each record in a member classes table represents a specific member attending a specific class. For example, if member M001 attends class C101, the member classes table would store M001 and C101 in the member ID and class ID fields respectively. This allows us to easily query the database to find out which members are in which classes or which classes a particular member is attending. So to summarize, when you have a many-to-many relationship, you need a linking table to manage the relationships between the two entities. The linking table will contain the primary keys of the other tables as foreign keys, and it will sit in the middle of the two tables you're linking. Before we wrap up, let's recap the key points we've covered in this video. First, we talked about what a database is, an organized collection of data that allows for efficient storage, retrieval, and modification of information. We also discussed the difference between flat file databases and relational databases, and why relational databases are more powerful for managing complex data. Next, we covered some important database terminologies like entities, attributes, primary keys, and foreign keys. We also talked about entity relationship diagrams or ERDs, which are graphical representations of the entities in a database and how they relate to each other. We then moved on to database normalization, which is the process of organizing data to reduce redundancy and improve efficiency. We also discussed referential integrity, which ensures that the relationships between tables remain consistent. Finally, we talked about many-to-many relationships and how to handle them using linking tables. We looked at practical examples like a gym database and a subscription service to see how these concepts work in real-world scenarios. So there you have it, a comprehensive introduction to databases. I hope this video has helped you understand the key concepts and how they all fit together. If you have any questions or topics you'd like us to cover in the future videos, leave a comment below and don't forget to like and subscribe for more computer science tutorials. Thanks for watching and I'll see you again in the next video. Bye for now.